What is containerization? Containerization is a technology that allows you to package and run applications and their dependencies in isolated environments called containers. A container is a lightweight, standalone, and executable unit of software that includes everything needed to run a piece of software: code, runtime, libraries, and system settings. This ensures that the application will run the same regardless of the environment it's deployed in. TAD, key concepts associated with containerization. 1. Containers. Definition. Containers are lightweight, portable units in which applications can run. They are isolated from each other and from the host system. Characteristics. Isolation. Each container operates independently with its own file system, network interface, and process space. Immutability. Containers are often built from immutable images, meaning that once a container is created, it doesn't change. If updates are needed, a new container image is created. Portability. Containers can run consistently across different environments, such as development, testing, and production, whether on premises or in the cloud. 2. Container images. Definition. A container image is a static file with everything needed to run a container: the application code, runtime, libraries, and dependencies. Characteristics. Layers. Container images are built-in layers, with each layer representing a different stage in the build process, e.g. base OS, libraries, application code. Efficiency. Layers are reusable, so multiple images can share the same layers, reducing redundancy and saving storage space. 3. 3. Docker. Definition. Docker is a popular platform that uses OS-level virtualization to deliver software in packages called containers. Components. Docker engine, the runtime environment that allows you to build, run, and manage containers. Docker Hub, a cloud-based registry service where Docker users can share container images. Dockerfile, a text file that contains a series of instructions on how to build a Docker image. 4. Container orchestration. Definition. Container orchestration is the process of managing and automating the deployment, scaling, and operation of containers. Popular tools. Kubernetes, an open source system for automating deployment, scaling, and management of containerized applications. It groups containers into units called pods and manages their lifecycle across a cluster of machines. Docker Swarm, a native clustering and orchestration tool for Docker containers. 5. Microservices and containerization. Definition. Microservices is an architectural style that structures an application as a collection of small, loosely coupled services. But containerization is a natural fit for microservices, as it allows each microservice to run in its own container. Advantages. Isolation. Each microservice can run in its own container, ensuring that it does not interfere with other services. Scalability. Individual microservices can be scaled independently, allowing for more efficient resource usage. Container networking. Definition. Container networking refers to how containers communicate with each other, with other applications, and with the outside world. Networking models. Bridge network. Containers are connected to a common bridge, and they can communicate with each other using their private IP addresses. Host network. Containers share the host's network stack, making them directly accessible via the host's IP address. Overlay network. This allows containers on different hosts to communicate securely over a virtual network. Container security. Challenges. Isolation. While containers are isolated from each other, they share the same OS kernel, which can be a potential security risk if not properly managed. Image vulnerabilities. Containers are built from images that might contain vulnerabilities if not regularly updated. Best practices. Use trusted images. Always use images from trusted sources or registries. Regular updates. Continuously update and patch container images. Limit privileges. Run containers with the least privileges necessary to minimize potential security risks. 8. Persistent storage. Challenge. Containers are ephemeral by nature, meaning that any data stored inside a container is lost when the container is stopped or removed. Solution. Use persistent storage volumes that can be mounted to containers, ensuring data is retained even if the container is destroyed. Real-life use cases of containerization. 1. DevOps and continuous integration, continuous deployment, CI/CD. Scenario. A software development team needs to test code in multiple environments, e.g. Linux, Windows, to ensure it runs smoothly before deploying it to production. Containerization benefit. Developers can use containers to create consistent environments that mimic production, ensuring that code works the same way across all stages of development, testing, and production. This leads to faster and more reliable deployments. 2. Microservices-based applications. Scenario. An e-commerce platform is designed using microservices, where each service, e.g., user authentication, product catalog, payment processing, runs independently. Containerization benefit. Each microservice is packaged into a container, allowing the platform to scale individual services independently based on demand. For instance, during a sale, the payment processing service can be scaled up without affecting other services. Cloud migration. Scenario. A company wants to migrate its legacy applications to the cloud but is concerned about compatibility issues. Containerization benefit. By containerizing the legacy applications, the company can ensure they run consistently in the cloud, as containers encapsulate all the necessary dependencies, eliminating compatibility concerns. 4. Hybrid cloud. Scenario. A company operates in a hybrid cloud environment using both on-premises and cloud infrastructure. Containerization benefit. Containers provide the flexibility to run applications consistently across different environments, allowing the company to move workloads between on-premises and cloud as needed. 5. Edge computing. Scenario. An IoT company needs to deploy lightweight applications at the edge, such as on sensors or small devices, to process data locally before sending it to the cloud. Containerization benefit. Containers are lightweight and efficient, making them ideal for running on edge devices with limited resources. This allows the company to deploy and manage applications at scale on a diverse set of edge devices. Conclusion. Containerization has revolutionized how applications are developed, tested, deployed, and managed. By packaging everything an application needs into a single portable container, it ensures consistency across environments, facilitates microservices architectures, and supports modern development practices like CI/CD and DevOps. As organizations increasingly adopt hybrid and multi-cloud strategies, containerization will continue to play a crucial role in enabling agile, scalable, and efficient IT operations.